In this paper, we introduce mesh pre-training with transformers for human pose and mesh reconstruction. Pre-train on large amount of dataset is very helpful for performance improvement on target task with small datasets. This has been very successful in various domains, including computer vision, natural language processing, vision, and language. Inspired by this successful improvement, people are interested in applying similar approach to the human pose and mesh reconstruction task. However, when applying such pre-training idea to the human pose and mesh reconstruction problem, we observe some challenges. First of all, there are a limited number of image mesh pairs. Although we have large amount of MoCap dataset, the MoCap dataset does not have images available for image mesh pre-training. To address the challenges, researchers have proposed to collect large-scale synthetic data by using the graphic rendering engines. However, this approach usually have the domain gap issues. On the other hand, researchers have also explored the adversarial training by using the generator and discriminator. However, this approach usually requires image mesh pairs to train the generator. We think there are several open research questions in these directions. First, how to efficiently leverage MoCap's dataset for pre-training the transformer at a large scale. Secondly, with such large-scale pre-training, can we improve the state-of-the-art performance? Finally, given such pre-training technique, can we enable a zero-shot capability on real images without any fine-tuning? This is the overview of the proposed mesh pre-training. Given a human mesh, which is sampled from the MoCap datasets, we first project its 3D human pose to the 2D by randomly selecting a virtual camera. After that, we synthesize the heat maps to represent the projected 2D human pose. Our mesh regression transformer takes 3 types of input tokens, including joint queries, vertex queries, and MoCap-generated heat maps. We then pre-train the transformer to predict the 3D coordinates of body joint and mesh vertex given the input tokens. During pre-training, we perform Masked Heatmap Modeling and Masked Vertex Modeling to improve the robustness of the mesh regression transformer. To be more specifically, we use the A-mask MoCap for pre-training. The dataset has 25 million frames. Each frame has a human mesh. We then sparsely sample 2 million mesh from A-mask for training. After the projections with 4 virtual cameras, we obtained in total 8 million human mesh for the pre-training. This is a summary of our pre-train fine-tune strategy. First of all, in our proposed mesh pre-training, we first pre-train the mesh regression transformer using MoCap-generated heat maps to learn human pose and shape knowledge. After the pre-training, we use an off-the-shelf 2D pose model to extract pose features maps, which are then fed into the mesh regression transformer. Through end-to-end fine-tuning, our model learns to reconstruct 3D human pose and mesh from the input image. We compare our method with the existing state-of-the-art approach on human 3.6 million and 3D-PW datasets. We present our pre-train and fine-tune results in the table 1. Our method outperforms the previous works on both datasets, including the recent transformer-based approach. It is worth noting that the recent approach, CLIFF, was a state-of-the-art approach on the 2 datasets. CLIFF additionally leveraged the camera focal length and the bounding box information to calculate the 2D reprojection loads on the non-cropped image. In contrast, our method does not have such post-processing, but still achieve better results, especially on the MPJPE. We demonstrate the flexibility of our method on 3D hand reconstruction, and we conduct experiments on the freehand dataset. Since there is less mocap data for the 3D hand, we use a recently proposed synthetic dataset called complement for pre-training. In this table, we show the performance comparison with the previous works. Our method outperforms the previous state-of-the-art method, including MoCap-generated, which also used the complement as pre-training data. We study whether our pre-training is useful for performance improvement. We conduct experiments on the human 3.6 million dataset, and Table 2 shows the results. We found that when pre-training and then fine-tune on the human 3.6 million dataset only, our method can achieve 35.5 PA MPJPE, which is better than the one without pre-training. We also observe similar findings when fine-tuning on multiple datasets. We study the impact of MPT during fine-tuning. On the left-hand side, we show the result. We first perform a one-epoch fine-tuning on human 3.6 million dataset and report the result for each fine-tuning step. The figure shows that with our pre-training, the fine-tuning converged better than the one without pre-training. On the right-hand side, we study the fine-tuning with less training data. We select 0.1%, 1%, and 10% of the human 3.6 million training data for fine-tuning, respectively. On the right-hand side, the figure shows that our pre-training helps improve learning performance when less data is used during fine-tuning. In summary, we introduce the mesh pre-training. It is a simple yet effective pre-training strategy that leverages large-scale mocap data to pre-train the mesh regression transformer for 3D human pose and mesh reconstruction from a single image. We introduced the use of MoCap-generated heatmaps with the Masked Heatmap Modeling for the pre-training. In our experimental results, we show that our method achieves better results than the previous state-of-the-art, including on human 3.6 million dataset, 3D PW, and freehand dataset. We also show that our mesh pre-training approach can be directly applied to real images without fine-tuning on any image mesh pairs.